Welcome to How to Build an Open Source Robot. My name is Bjørn Ivar Teigen, and I study robotics at the University of Oslo. I'm here to talk to you because I'm a member of Mikros Konstruksjonslag, which is a student organization or a student association that builds robots on our spare time. And these are our sponsors. And this is our robot. You can come look more closely at the robot at the UIO stand, which is straight across from the main stage here at the west side of the ship. So, in order to build a robot, you need a computer because a robot is an automated mechanical system, and the computer is the brain which does the automation. And for this purpose, I recommend using a Raspberry Pi. We used this for our first prototype, and also for our main robot for quite a while. It's about $50 or 400 kroners, and it's perfectly capable of running Ubuntu Linux, which is the operating system. It's got a quad-core processor at 1.2 gigahertz, and it's cheap, and it's got a vibrant open source community, meaning that whenever you encounter some sort of problem, there's most likely someone who's already solved that and put it online, so you don't have to figure it out all by yourself. And the Raspberry Pi has general purpose input and output pins, meaning that you can control sensors and low-level hardware directly. But I recommend using an Arduino, which is a cheap open source microcontroller. And the Arduino is different from the Raspberry Pi in that the Arduino does not have an operating system of its own. It's running a simple process that you can program. And what we do is to communicate with the Arduino via USB from the Raspberry Pi. And the Arduino is perfect for controlling motors or servos or reading sensor data. So, and it's very flexible, so you can have it do whatever you like, basically, as long as it's not too big of a task. We then upgraded to a Jetson TX1, which is slightly more expensive. It's about 6,000 kroners. But if you're a student, you can buy it for about half that if you apply for an academic license. It's got a built-in GPU, which we use for computer vision purposes. But I suggest starting with a Raspberry Pi if you're going to sort of try out robotics as a hobby or for some project, because it's cheap and it's a lot easier to use. So, on the software side, we use Ubuntu, and that's because we use ROS, which is Robot Operating System. And Robot Operating System is sort of a meta operating system that sits on top of Linux, and which provides sort of program-to-program communications automatically, so that you don't have to do all of the sort of nitty-gritty protocol and communications programming yourself. You can just have your have ROS do all of that for you, which makes robotics a lot easier, because typically a robotic system has a lot of sort of isolated programs or processes running at the same time. So you'd have one program reading a camera and one program which controls a motor, and then you want those two to communicate. But you don't want to do everything in one program, because that's hard to maintain, hard to write, and also very hard to distribute if you won't have to do some processing on one computer and then some processing on another computer. So ROS makes that simple. ROS is very widely used in the robotics community among researchers and also businesses. These are some of the examples. So this is the Robonaut 2, which is NASA's robot, or one of NASA's robots. It sits on the, or one of these are on the International Space Station, and that runs ROS. This is the PR2, which is a robot made by Willow Garage for sort of robotic scientists to experiment on. Then it's the Parrot drone, which you've probably seen. It's pretty common and very cheap. And you can also put ROS on this and make it a lot more capable. So you can make it able to fly automatically, or you can incorporate sensors that it doesn't already have and stuff like that. Then this is the Pioneer from a company called Blue Eye, which is a Norwegian startup, Blue Eye creates underwater drones. So you can buy one of these, and you can remote control it underwater down to 150 meters depth. And that robot as well runs ROS. And this is a rover type. Just for completeness, this is robots in the ocean, in the air, on the ground, and in space. All enabled by ROS. So now I'm going to tell you a bit about how ROS works. So the top node there is the sort of main core ROS program. It's called the master node, and its job is to set up and organize all the other communications in the system. So we have two nodes here, one talker and one listener, and they don't know about each other. They're just separate programs which can be running on separate machines. Doesn't have to, can be on the same machine, but it's very flexible like that. And the way ROS works is to set up communications. So each node tells the master node what information it wants. So the talker lets the master node know that he wants to publish messages on a topic called chatter, and the listener tells the master node that he wants to subscribe to messages on the topic called chatter. Then the master node creates the topic and tells the talker and the listener where to find it. And then the communications with the master node is removed. So now the talker is talking directly to the listener on the topic called chatter. And the master node knows where the topic is, and so that if there are any more nodes who wants to either subscribe to or publish to that same topic, then the master node will organize that and set it up. So I think I'll do a demo of this. If I, let's see. So let's just remove these and set up everything from scratch. So here. So this first terminal, I'll run the ROS master using the command ROS core. Then here I'll run, so ROS run and it's in the package called ROS.py tutorials, and it's called listener. Okay, thanks. I'll wait. So what I'm doing now is to set up the listener node. So now I've started the listener, and it's told the master that it wants to subscribe on a topic called chatter. But there are no messages published there yet. So it doesn't receive any data. And we can visualize that using this. This is a tool which comes with ROS for inspecting how the nodes and topics are set up. So what we've got here is a single node with no topics, because the topic hasn't been created yet, because there are no publishers. So I'll just keep this down here. Then we'll run the talker. And you see that the listener now receives data. And we can visualize this using the graphing tool. And see that now we have one talker, the topic chatter, and one listener. And this is the sort of the basic sort of concept in ROS, is that you divide your program up into different nodes and have them communicate on different topics. And doing that or setting it up is very, very simple. It's a few lines of Python or C++ code. And for those of you familiar with sort of computer communications, having a system that can do that automatically over multiple machines in a network and stuff like that is very, very useful. And then when it comes with these tools for introspection and visualization as well, it's really becomes very, very powerful. So let me just shut these down, and then we'll continue with the presentation. So here. So this is the robot that, or the first prototype that we built. And it's, I think, a great example of a very, very simple robot that still uses all of the important pieces of ROS. So this consists of a Raspberry Pi, an Arduino, a web camera, and a battery and 2 motors. And the entire sort of hardware package for this costs maybe about 2,000 kroner or something like that. And it's completely homemade, and you can also very easily extend on it if you want to have more stuff. So you could add servos and make the camera tilt or pan or anything like that very, very easily, because it's all set up with ROS. So this is the sort of complete organizational chart of the software system, and the hardware system. We usually want to have some sort of way to visualize the system from a desk and not having to plug the robot into a monitor and keyboard and mouse all the time. So what we did is to have ROS running on both a laptop and the Raspberry Pi on the robot. And then we'd run code to talk to the Arduino, which talks to the engines or the motors, and also the camera on the robot. So all of the things that are in the sort of box here is running on the robot. And then we have ROS on the laptop as well, so that we can view the camera stream or send commands to the robot so we can remote control it and stuff like that. And this system is, I would say, pretty simple to set up, sort of depending a bit on how much experience you have with Linux and programming in general. But it's entirely doable, even if you have very little experience. It just it takes a bit more work. So once you then have a robot, you have a basic setup with a laptop and a robot with a Raspberry Pi, and it's capable of driving around as long as you send it some commands. You may want to do some more advanced stuff, and that means adding more sensors. So ROS comes with packages and drivers to talk to various sensors. It's become quite an extensive ecosystem after now it's 10 years, I think. So it's very simple to set up communications with, for instance, Microsoft Kinect or stereo camera. This is one of the cameras that we have on our robot. This is an inertial motion unit, which is a gyroscope and an accelerometer. So this sensor keeps track of where the robot is and how fast it's moving, and that enables the robot to build maps. So if you have either images or laser scan data and a very detailed position or very detailed position information, then you're able to build maps. So going from a robot that is very, very simple, having just 2 or 4 motors and having to be remote controlled, to having a robot that's capable of autonomous mapping and navigation, is a matter of setting up pre-existing ROS nodes that are built by companies or scientists or master students around the world, and putting out some cash for the sensors, or buying a readily available robot. So these are the TurtleBot series. They are very well supported robot platforms, which makes setting up a robotic system a lot easier, because hardware is very often sort of the bottleneck time-wise, because building robust hardware systems is very complicated, especially if you're primarily a software engineer. So if you don't have the time or the skills to build a hardware system, then buying one is a great option. And then when you have a robot that's mechanically stable and you've bought some sensors and you've set up the system, you've got a robot that's capable of mapping its environment in 2D or even 3D, and then you're able to do stuff like having your robot autonomously drive around your home. You can register points in the map so that it knows where stuff either is or is supposed to be. You can have it clean up stuff or scare a cat every time it's in the sofa or something like that. And that's the goal of our robot project in the Mikros konstruksjonslag, which is to have a robot become completely autonomous and being able to navigate around the university and guide people to rooms or take our trash out, stuff like that. So I considered going into even more detail on the software side, but it very quickly becomes a lot of information. So if anyone's interested in more sort of the mapping part or more advanced ROS features, please stop by our stand afterwards and have a look at our robot and ask all the questions that you want. And I hope that I've convinced you that building a robot is a complicated task, and you shouldn't try to do everything by yourself. Embrace the open source community and take advantage of all the really great infrastructure and software and community that already exists. And you'll be able to do very cool things very quickly. So thanks.